Hello students, welcome back to JCE Connect series of lectures. We'll continue some more numerical problems on a Pelton wheel. So let us take the first problem. The following data were obtained from a test on a Pelton wheel, and the data given here are: head at the base of the turbine 32 meter, discharge of the nozzle 0.18 meter cube per second, area of the jet 7500 square millimeter, power available at the shaft 44 kilowatt, mechanical efficiency 94%. Calculate the power lost in the nozzle, in the runner, and in the mechanical friction. Okay, so this problem is a bit different from the previous one. So here when the turbine is being developing a power, and they are asking to calculate what is the power lost in the nozzle, runner, and the mechanical friction, that is in the shaft. So here these are the data given, that is head available is 32 meter, discharge through the nozzle also given, then the area of the jet is also given, the power available at the shaft is also given, then the mechanical efficiency, then they are asking you to calculate the power lost in the nozzle and the power lost in the runner, and also mechanical friction. Let us calculate first the power at the base of the nozzle. So this power is required when we that is for calculation of overall efficiency and all. So we need to calculate what is the water power at the base of the turbine. So water power can be given as gamma W Q into H. Then gamma W, as we know, it is a specific weight of the liquid, that is 9.81. Since here the liquid is water, the water specific weight is 9.81 kilonewton per meter cube. Q is also given in the problem, that is 0.18 meter cube per second. Also the head available is 32. Substitute, we get water power as a 56.5 kilowatt. This much power is being transferring at the base of the turbine. Means this power, this water power, this jet power we have calculated, that is water power. Okay, so that is water power is 56.5 kilowatt. Then let us calculate next velocity of the flow through the nozzle. As we know, Q equal to A into V, then V equal to Q by A. Then area is given, the area of the jet is given, substitute here, then we get as a 24 meter per second. Then power at the nozzle exit. The actual water power is available for us is 56.5 kilowatt, but once it coming out of the nozzle, so it will be having certain losses at the nozzle exit. Then that is the kinetic energy of the jet. Then power at the nozzle exit will be half rho A V cube. Then half, that is rho is 1000, density of water, then the area of the jet, then the velocity. Then this much is the power available at the exit of the nozzle. Okay, here at the exit of the nozzle, this much power is available. Okay, so this is the penstock, and this is the nozzle. So at the exit of the nozzle, the power available is this much, 51.84 kilowatt. But the water power is how much? 56.5. Then this much is the water power, and this is the power available at the exit of the nozzle. Hence the power lost in the nozzle. So how much power has lost in the nozzle? That is water power minus the nozzle power. That is power lost at the nozzle, then we get 4.67 kilowatt. This much power is being lost in the nozzle, that is power lost in the nozzle. Always the water power will be more than the power available at the exit of the nozzle. Okay, next, this power supplied to the runner that is power supplied to the runner, is equal to the kinetic energy of the jet. So whatever the power available at the nozzle exit, so whatever power available at the nozzle exit, that same power is being transferring to the runner of the turbine. Okay, power supplied to the runner is given to the kinetic energy of the jet, that is this much, the same is being transferring to the runner. Means the power available at the nozzle exit, the same power is being transferring to the runner, this runner, through the buckets. Okay, so 51.84 will be the power available at the runner. Then the power developed by the runner will be what? As we know, overall efficiency or the mechanical efficiency can be given as, mechanical efficiency will be what? Shaft power divided by runner power. This is mechanical efficiency, power available at the shaft divided by runner power. Then from this one we can easily calculate the power developed by the runner will be shaft power by mechanical efficiency. So in this problem mechanical efficiency is given, substitute here, we get the power developed by the runner will be 46.81 kilowatt. So this is the power supplied to the runner, but while supplying this power to the runner, some of the losses will take place. After losses, whatever the power developed by the runner will be this much, 46.81 kilowatt. Now the power lost in the runner, power lost in the runner will be what? Power available at the exit of the nozzle minus power available at the runner, that will be giving power lost in the runner as 5.03 kilowatt. Then the next is power lost in mechanical friction. Power lost in mechanical friction. So already we know the power available at the shaft. Power available at the shaft is been given, that is 44 kilowatt. Means, so in this one, first power is comes water power, then the next the power at the nozzle exit, then the power at the runner, then the runner, after the runner power to the shaft power. But here the power available is how much is been given in the problem, that is 44 kilowatt, and we know the power available at the runner. Then the power lost in the mechanical friction will be 46.81 minus 44, that is runner power minus shaft power. We get as 2.81 kilowatt. We get 2.81 kilowatt. Then the next will be as a check on computation. So we have calculated all the power lost. So if you want to do the check, as a check on the computation, the difference of power at the base of the nozzle and the power available at the shaft must be equal to the sum of the power lost in the nozzle, in the runner and in the mechanical friction. I'll repeat, as a check on computation, the difference of power at the base of the nozzle and the power available at the shaft must be equal to the sum of the power lost in the nozzle, in the runner and in the mechanical friction. Thus, water power minus the shaft power, that is 12.51 kilowatt. Then sum of all the losses, that is 4.67, that is the power lost in the nozzle, 5.03 power lost in the runner, and 2.81 power lost in the mechanical friction. So when you add all together, you will get again same 12.51 kilowatt. Directly, that is a water power minus shaft power gives you the this much lost, that is loss. Then when you add the stage wise losses, 4.67, the power lost in the nozzle, power lost in the runner, power lost in the mechanical friction, we get the same. Hence whatever the value we have calculated above, they all are correct. Okay, so let us take one more example. A Pelton wheel has a mean bucket speed of 12 meter per second and is supplied with a water at a rate of 750 lps under a head of 35 meter. If the bucket deflects the jet through an angle of 160 degree, there is angle of deflection, find the power developed by the turbine and its hydraulic efficiency. Take coefficient of velocity as 0.98, neglect friction in the bucket. Also determine the overall efficiency of the turbine and its mechanical efficiency is 80%. Okay. So in this problem, they are asking you to calculate the power developed by the turbine and its hydraulic efficiency. Calculate first the power developed by the turbine is given by, so we know the formula, that is the runner power formula, rho a v1 into bracket v1 minus u into bracket 1 plus k cos pi into u. This formula already we know, so and we have derived also this formula in while deriving work done and efficiency of a Pelton wheel. And where a into v will be the q into bracket v minus u into 1 plus k cos pi into u. So here where k is the friction, that is coefficient of friction in the blade passage. So q is given here as 750 lps, that is 0.75 meter cube per second, and also the density of water is 1000 kg per meter cube. Then the velocity of the jet can be calculated cv into root of 2gh. Then we get this much, 25.68. Then velocity of the bucket is given 12 meter per second, and take k value as a 1 for neglecting the friction in the buckets. Then the angle of deflection is given as 160. Then the angle of Vane at exit will be 180 minus 160, that is 20 degree. Then the cos pi will becomes 0.9397. Thus, by substituting, we get as P equal to 1000 into 0.75, directly we get 238.815 kilowatt. So this problem is without drawing the velocity triangle. So we are calculating just by using the final equation of work done, or the force work done per second of a Pelton wheel. This formula we know while deriving the equation. We have got this formula. You have to use this formula to calculate here. Then we get the power to 38.815 kilowatt. Now the hydraulic efficiency again you can calculate by using a runner power by water power. Since he has to calculate water power, the net head is not been, sorry, the under the head of, so head is been given. So you can calculate by using runner power by water power also, or else if you remember this formula, you can use this formula and calculate the hydraulic efficiency here. So when we use this formula, then we get the final answer as 96.6%. Okay, substitute all the values here. Okay, we get 96.6 percentage. Okay, then the overall efficiency of the turbine, as we know, the overall efficiency will be hydraulic efficiency into mechanical efficiency. Hydraulic efficiency we got as 96.6, 0.96 into 0.8, we get as overall efficiency 77.3 percentage. Okay, so as I said, the hydraulic efficiency can also be calculated by using runner power by water power. Okay, so as this is the runner power we got, then the water power as you know, gamma w q into h. So if you know the value of q, that is also given, then substitute here, we get a water power, then runner power by water power gives you the hydraulic efficiency. The overall efficiency can be calculated. The overall efficiency will be the hydraulic efficiency multiplied by mechanical efficiency. So we get as a 77.3 percentage. Okay, so I hope you understood this type of problems. Okay, please practice this type of problems. They are very, very important. So you can refer any textbook and just keep on solving the problems. You will understand the problems. Thank you.